Today, let's go over a medium question that's in the premium category that I just solved. I actually struggled with this quite a bit and got time limit exceeded until I was finally able to come up with an approach. So let's try to do it. So you're given three different arrays of integers, and here you know that monsters and coins are the same length because if you defeat this monster, you get this award. If you defeat this monster, you get this award. If you defeat this monster, you get this award. If you defeat this monster, you get this award. And if you defeat this monster, you get this award. Right, so that's why these are the same length. And essentially, any number in heroes that is bigger than or equal to the same number in monsters gets whatever award, as you can see. And you want to basically return an array denoting how many coins this hero can collect. So 4 is bigger than 1, 1 and 2, 3, so you would add 2 plus 3, which is 5, plus 5 plus 6, which is 11. 5 plus 11 is 16. For 2, you would add 1, 1, and also 2 because it's bigger than or equal to. So 2 plus 3 is 5, 5 plus 5 is 10. There you go. Cool, so let's start by mapping the monsters to the coins. Let's create a dictionary for that. And let's create a list because, as you can see, one monster can collect multiple coins. So let's iterate over monsters im in enumerate monsters and dm dot append coins of I, right? Because it has to line up. This guy only collects this. This guy only collects this. This guy only collects this, vice versa. And then let's sort them by their keys because we want to eventually binary search on the monsters. And we also want to keep track of the sum up to a current number. So let's say d equals dict sorted d.items key equals lambda x0, which is just sorting by the keys of the dictionary in ascending order. So let's print d. Okay, so you can see this sum is 5, which is important later. And now let's keep another dictionary called sumd. This is going to keep track of the prefix sum, the current sum up to the current point, because as you know, the keys increase, the sum gets bigger over time, right? So not necessarily meaning that like 5 has to be bigger sum than 3, but when you get to 5, it has a bigger cumulative sum than 3. So for k and d, let's call this sum up to this point equals 0. And sum up to this point plus equals to sum of dk, right? dk is the sublist, so we're summing this up, so it'd be 5. So just let's print this and sum up to this point. So you should see 1, 5, 2, 10, 3, 16, and so on. Sum up to this point. 1, 5, 2, 10, 3, 16, and 5, 20, right? Even though this is less, it has a bigger cumulative sum because you're still adding 4 to 16. And now let's put this in our sumd. So sumd k equals to sum up to this point. Let's print sumd. So sumd, cool. Now we can figure out what we need to do, which is to find the maximum coins the heroes can collect. So to do this, this is the binary search part. You can use like the bisect module for this, but I don't really know how to do that, so I'm going to do it my way. So first of all, binary search means that we're actually trying to reduce. Binary search generally means you have to sort the array, but in this case, we're not going to sort heroes, we're going to sort monsters, because monsters is going to be the one we're binary searching on. So monsters is going to be 1, 1, 2, 3, 5. And then for each hero, we're going to find like the perfect pivot point. So for example, for 1, we're going to look here and we're going to say this total cumulative sum is 5, right? For 4, we're in between 3 and 5. So only 3 is included. So we're going to say it's 16. And for 2, sorry, we're going to simply say it maps to 10, because this only gets bigger as we keep going, right, from left to right. And now we can do what we just said, which is for agent heroes, because you can see the result lines up. It wants this guy's ability to collect coins, this how many coins this guy can collect, right? And now we can run our binary search, which is, let's sort monsters first in ascending order, and then let's declare left and right pointer at the end of monsters. So we're going to do this, left and right, and we're going to try to find the best position for H being less than or equal to H. So now we can say if left is less than or equal to right, mid equals to left plus right divided by 2. This is an index. So now if monsters of mid is less than or equal to H, then, or let's do bigger than H, because that's the wrong condition. It's just easier for me to do it that way. Right equals to mid minus 1. Else, now we can say best possible equals to 0, because we want to keep track of whatever that was. If we binary search and we find 1, but we can still go up to 3, we put 1 in there. If we can binary search up to 2, we can still go up to 3, but we're never going to cross over 3, right, if we're looking for 4, because that's what this condition does. So next, if it's less than or equal to, then best possible equals to max of best possible, right, because this only gets bigger in terms of the values between best possible and monsters of mid, right, because that's the actual value we're looking for, and it's not bigger than H, which is H is this. And then left equals mid plus 1, because now we're trying to move the left pointer in this direction to find a bigger potential until we get to this, which is 4. So we're going to go back and we're going to say like 3 is the best, right? Best. And then at the end, let's print best possible, and then let's print next turn. So as you can see, 1 is the best for this, which is going to be 5. 3 here is going to be 16. 2 is going to be 10, right? So now our life is a lot easier. We want to return an array of integers. So if best possible is bigger than 0, then we can do this, which is going to be result.append sumd of best possible, right, which is like 3 in this case. Just going to map to 16. If that's not, then we're just going to append 0, because the hero cannot collect any coins. And then at the end, we can just return the result, I think. There you go. So it passes all test cases. It doesn't get time limit exceeded. Before, I used to use like an O of n squared solution that would like pass 707 out of 712 test cases, or 703 out of 76, so that's pretty frustrating. I basically just did I unnecessarily looped. I didn't take advantage of the binary search, so this is a better approach. And yeah, so I hope this video was helpful, and stay tuned for more. Thank you.